Okay, I am going to attempt to explain something that I discovered yesterday that has made it easier for me to understand tuning systems. So, the example that I'm going to give is with my D string. And I actually have this written down over here, but I'm going to try and explain it as I write it down. So actually I wrote down D3, which I don't think that's right, but we'll take D3 as an example. This is the fundamental. This is 146 hertz on a string. There's a set length. It cuts off here, and it cuts off here, and the rest of the string is not involved in this equation. So when you vibrate this string, it produces 146 hertz. If I were to put my finger right here and lightly press, not all the way down, and play, it would produce a harmonic that would multiply this frequency by 2. Now we have 292 hertz. Yes, Cinnamon, I hear you. Hold on. Alright, I'm going to attempt to do this with a cat on me. And if you don't know, multiplying any frequency by 2 is the same as creating an octave's distance between them. And with each partial, which is what we call these harmonics, we are multiplying this fundamental 146, the original string, by whatever number that we are dividing the string by. So in this situation, we are dividing the string by 2. I put my finger exactly halfway across the string. This multiplies the frequency by 2. So what happens if I split this into thirds? If I put my finger here, or if I put my finger here? This, if I put my finger here, will be 146 times 3, which is 438 hertz, or a 4. And so we can keep splitting this up into different divisions, into fourths, into fifths, into sixths, and multiply it by however many sections we've created. We've created 2 sections by splitting it in half, right? Here's 1 section, here's 2 sections. That multiplies the frequency by 2. We split it into thirds. If we put our finger here, or if we put our finger here, that multiplies it by 3 because we have these 3 sections. That makes enough sense to me, but I never really thought of it that way. I always just thought the further you go up, here's the octave, here's the fifth. What's next? It's actually another octave. So if we take 438 and add another 146, then we get 584. And that means we're now on D5. And you'll notice that this is also an octave because we're multiplying by 4, which is the same as multiplying by 2 and multiplying by 2 again, which means we are going an octave above this. Next is the weird one. There are some other weird ones, but next is, if we add 146, we get 730 hertz. So this is splitting it in half. This is splitting it into thirds. This is splitting it into, oh, sorry, I actually messed this up. This is the fundamental. We're splitting it into one. We're not splitting it at all. This is the first partial, splitting it into two. This is the third partial, or this is the second partial, splitting it into three. This is the third partial, splitting it into fourths. And then this is the fourth partial, splitting it into fifths. And 5 is a prime number. I don't know if that actually is related, but I mean, 3 is also, these are all prime numbers except for 4, but I don't know. 5 is different because this is an F sharp 5. But if you were to play 730 hertz, it would be flat in terms of equal temperament. Because the way equal temperament is you have your fundamental, and instead of having these ratios where, you know, you multiply by 3 or you multiply by 4, you're really just multiplying this fundamental by 2 to the power of whatever chromatic scale degree you're on. So if I were to take a third, then F times 2 to the scale degree of 5 out of 12. And so if F is 146, and we're multiplying it by 2 to the 5 out of 12, that comes out to be slightly more than 730 hertz. And I don't remember what the number is. But regardless, the big realization that I came to, if I can make sure I have enough time here. Okay. The big realization that I came to is the pattern that this harmonic series has. Because if you understand the math of this, you were taking 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 until theoretically infinity. And so if I just write down the rest of what I have on this other piece of paper, we have A5, we have C6, D6, and E6. And I wrote some more, but it's not really necessary for this demonstration. So these are all just multiples of 146. And of course, we have first, second, third, fourth, fifth partial, sixth partial, seventh partial, eighth partial. Ooh, I ripped the paper. And we're multiplying by 9, 8, 7, 6. And you'll notice 8 is a multiple of 2. Well, so is 6, but 8 is 2 times 2 times 2, making this another octave, D6, back to D5, back to D4, back to D3. But you'll see there's no, there are no partials in between these two. There's 1 in between this octave. There's 3 in between this octave, and you can imagine how many there are in between this and D7. So what I realized, which is kind of makes sense why we have equal temperament, because if you go from D3 to D4, that's an octave. And then here is a perfect fifth. And then here is a perfect fourth. And then this is a major third, right? And then this is a minor third. And then this is another minor third. And this is a major second. And this is a major second. And the issue here is the pattern is that the distance is getting smaller and smaller. The intervals are getting smaller and smaller because the higher up in frequency you go, the less this represents. So if we're going from an octave down to perfect fifth, down to perfect fourth, the major third, a minor third, it's getting slightly smaller each time. So by definition, this minor third and the other minor third can't be equal. They are slightly different intervals, even though we recognize them theoretically the same. And then we go to a minor second, or a major second, and then we go to another major second. Well, these two are also different. So if we have one string, the D string, that's great. But we have multiple strings. We have 4 strings on a double bass, which is what I'm using as a reference. And on a piano, you have hundreds of strings, right? So how the hell can we make all of this in tune with each other when everything is different in these octaves? So that's why we have equal temperament, I think. It's more complicated than this. But that realization was so big for me that, oh my God, it's going down in intervals, which means that these two intervals can't be equivalent. And these two intervals also can't be equivalent. But in equal temperament, they are. It's crazy.